So what if I told you that the secrets of the most violent events in the cosmos, we're talking colliding black holes, aren't just out there in the stars, but are actually hidden in the faint glow of a single atom? It sounds like science fiction, right? Well, today we're diving into a brand new theory that could completely flip how we listen to the universe.
You know, our whole story today really begins with a hidden signal, a cosmic message that's been encoded in the light from the most basic building blocks of matter. I mean, for more than 100 years we've been studying this light, but it seems we might have been missing something truly extraordinary this whole time. I mean, just pause and think about that for a second. Instead of building these massive detectors that are the size of small cities, what if we could sense these huge cataclysmic events using something, well, almost infinitely small? This is the wild, mind-bending idea that's at the heart of the new theoretical study we're breaking down today.
Okay, but to really get how revolutionary this new idea is, we first have to talk about how we listen for these cosmic whispers right now. And trust me, it's a story of some absolutely incredible engineering and, frankly, mind-boggling precision.
So what are we even listening for? Well, these things called gravitational waves. And they're not just waves in water or air, they are literal warps in the fabric of reality itself. When two black holes smash into each other, they send out these ripples across the entire universe. Trying to detect them is like, I don't know, trying to feel the vibration from a feather landing 1,000 miles away. It's that subtle.
And this slide just lays it out perfectly. On the left, that's what we do now. We build these massive, kilometers-long instruments that use powerful lasers to measure teeny tiny changes in distance as a wave passes by. But on the right, that's the new idea, a sensor that could be just millimeters across. And instead of measuring distance, it looks for changes in light itself. I mean, the difference in scale is just staggering.
So how on earth could a tiny sensor like that actually work? Well, to figure that out, we need to zoom way, way in. We're going to shrink our focus from the cosmic down to the quantum and look at one of the most fundamental processes in the entire universe, how an atom creates light.
It's really like this beautiful, simple little dance. First, an atom gets a jolt of energy. You can think of it as getting excited. But it can't stay in that hyper state for long. It wants to relax. So it quickly drops back down to a lower energy state. And to do that, it has to spit out that extra energy. And it does that in the form of a tiny particle of light, a photon.
Now this whole process has a name, spontaneous emission. But the really interesting part, the bit you need to remember, is right there at the end of the definition. The whole thing is driven by the atom's interaction with something called the quantum field. Just think of the quantum field as this underlying fabric of all energy and all particles. That right there, that's the key.
And right here is where it all clicks together. The scientists behind this new theory had this amazing thought. If gravitational waves are ripples in spacetime and atoms release light by talking to the quantum field that exists inside that spacetime, well, couldn't one affect the other?
But there's a puzzle. And this is the very reason this secret has stayed hidden for so long. It turns out when a gravitational wave zips past, it doesn't make an atom release more photons or fewer photons. The total amount of light, the brightness, stays exactly the same. So if you were just measuring brightness, you'd see absolutely nothing.
I absolutely love this quote from one of the researchers because it's just the perfect way to picture it. Imagine an atom is like a tiny speaker, and it's putting out this pure, steady hum. Normally, that hum sounds exactly the same no matter where you are in the room. But if a gravitational wave passes through, it actually warps the space, and it subtly changes the pitch of that hum. And this is the cool part. That change in pitch is different depending on where you're listening from.
And boom, there it is. That's the aha moment. The secret isn't in how much light the atom puts out. It's in the properties of that light. The passing wave subtly shifts the frequency, which we see as color, of the photons. And crucially, this color shift isn't the same everywhere. It creates a very specific directional pattern.
So this isn't just some faint, random blip. It's a rich, detailed fingerprint. By measuring this directional pattern in the light, scientists could, in theory, figure out exactly where the wave came from, its polarization, which is like its orientation, and, maybe most importantly, they could tell it apart from all the other random quantum noise. It's like a complete information package delivered by a single atom.
All right, so we have this incredible new theoretical tool. The mystery is solved, at least on paper. But what does this actually mean for the future? How do we take this really cool idea and turn it into a real working detector?
Just look at that. Millimeter scale.
Let that sink in for a second. We're talking about going from instruments that stretch for kilometers across a desert to a device that could potentially sit on a tabletop. This is the promise, right here, the ability to build tiny, compact, and maybe way more numerous gravitational wave sensors.
And, this isn't just pure science fiction. The researchers point out that we already have the perfect technology to test this: cold atom systems. These are the super precise guts inside atomic clocks, systems where we can control and watch individual atoms with unbelievable accuracy. This is almost certainly where the first experiments are going to happen.
Of course, we have to ground all this excitement in a little bit of reality. This is a brilliant, brilliant theoretical insight, but for now, it's still just that, a theory. The next huge step is to see if it's even possible in the real world. That means doing a really thorough noise analysis to see if this incredibly delicate signal can actually be picked out from the background chaos of the universe.
And that really brings us to the end. This whole discovery, this whole idea, came from looking at a process we thought we completely understood, but just from a totally new angle. It really makes you wonder, doesn't it? In a universe that is just packed with mysteries, what other profound secrets are sitting right in front of us, just hiding in plain sight, waiting for someone to ask the right question?